All right, what is a strain gauge? As the definition you see here is, in principle, is basically a resistor, like a wire resistor, right? And it's used to measure stress or a strain, and then after we know the strain, we can calculate stresses. Just to learn about its principle, suppose I have, before I get to that image that you see there, suppose I have a small wire. Now this wire, let's say, has a length L0, and let's say that this wire has a cross section A. And now let's say that I attach to this wire maybe simply to an electrical current, plus minus E. And there will be, let's say, we'll show typically minus plus. There will be a current going through that. And this one, let's say it has a voltage V. So this, and then there will be this current going through that wire. This wire has a resistance. That resistance can be calculated. We'll show it by R. So that's the resistance. And it depends on the density of the wire, whatever material we use, let's say copper, or maybe gold, or a different material. It depends on the length and depend on the area cross section. So that gives me the resistance. And also in past courses in physics, we learned that V is equal to Ri. There is a relation between voltage and current. Now, suppose that I attach this piece of wire to maybe a mechanical component, right? Something like that. Let's say it is maybe a plate or something. So we glue, let's say we glue that wire glued to the part. And now suppose that I apply a load to this part. Let's call that load F. So we learn in this course, if I apply load F, then there will be elongation, right? Or if the force is a compressive load, then it's going to be shortened, the components. As a result, since I glue the wire to the part, we know the wire also is going to become longer or shorter. So let's write it down. After applying the load F, the result is change in L0 and A, right? So this wire, its length is going to change, its cross section is going to change. And simply we know we are going to see there will be a change in R, the resistance, right? Because R simply is a function of L0 and A. Obviously, the density will not change. So it means that now I have a simple device which, if I measure either voltage or current and their change, now I have an indication that how L0 is changed, how A is changed, and I can relate them to a strain actually. That's in principle how a strain gauge works. So this is the principle. In practice, actually, instead of one wire, people use like several parallel wires, like similar, let's say if I want to make a strain gauge, I use this wire, like that wire, maybe that wire, and that wire. So instead of one wire, I use 4 wires, maybe the same length, everything's the same, like they are a little bit different here. Let's just copy them, make them all the same. And now simply I connect them. Let's say I connect that one with that, this one with that one, and that one with that. Right? So these are my wires length L0. And next, what I will do, I'm going to attach to that here to two other wires. Since this is very loose, so typically what people, they do, they put all these four wires on a, let's say, on a case, in a very thin case, which is typically is a polymer, like epoxy polyamide, as I wrote here, or like just any polymer, actually, to protect these wires. And the material that people use for these is typically copper, but for more expensive strain gauge is gold, which gives us a better result, actually. Now, what people do, this is a strain gauge, they attach it to the component. And now when we apply a load, if the length of these wires change, the result will be change in the voltage or current, as I showed it here. And we can calibrate it to get the result. All right, so this is the principle of a strain gauge. Here is an image of an actual strain gauge. So this is strain gauge, as you see, there are two wires which we use them to connect, like here, positive, negative current. We glue everything to the surface, so we'll get the strain gauge that we want. All right. But how it works, and maybe here I should stop and have some strain gauge. I'll show you. Let me again. I wish we were in the class and I could show you. Hope you guys can see my camera. So this is a strain gauge box. They are not very expensive, except this one. If it is gold, it's going to be expensive. And inside that, you will see different type of strain gauge, which I will show you. This is the one that you just saw the image, right? So that's an actual strain gauge, which it is in a protective case here. If I slowly be able to remove it. Okay. So you can see it better. So this is a strain gauge actually. All right. So these are the two wires which you can solder it to, like two wires, and you glue the entire things to the surface of the material that you want to measure the strain. Now let's go back, and I'm going to share my screen again. Share. I have to go back and forth several times and turn off the camera. All right. Coming back here. To use the strain gauge, so I'm just going to quickly check the chat here. Yes, the annotated slide will be posted as well. So to use a strain gauge, we need to use a circuit which is called the Wheatstone Bridge. I'm sure you've heard about the Wheatstone Bridge in one of your physics course before. Wheatstone Bridge is a circuit after the name of the scientist Charles, I believe Charles, or something like that, Charles Wheatstone. And some people call it Charles Wheatstone circuit or Wheatstone bridge. It looks like something like that. And it consists of three resistors, R1, R2, and R3, and our strain gauge. Remember, our strain gauge is also a resistor, right? I highlighted here, which has its own resistance. And when we buy a strain gauge in the document, it tells us what is the resistance. So the way it works, we need to build this actually circuit. I can use any R1, R2, R, but there is a relation actually. If let's say if I give a voltage, input voltage here, I'm gonna get an output voltage here, like from this VG. So this VG actually is what I measure. Maybe we use a voltmeter and what we measure. This is our input here. Let's say I give it 5 volt and depend on R1, R2, R3, and R gauge. Let's call this one R gauge or a strain gauge, and we'll show it by RG. I'll get the value. I'll write down the formula for you, so you don't need to go back to your physics course and check it. So the VG, the output voltage, will be equal to V input multiplied by R2 divided by R2 plus RG, our strain gauge, minus R3, R1 plus R3. Now, if R3 divided by R1 is equal to R2 divided by RG, it's called a balance bridge. Again, one of those things, perhaps you've learned it in physics. If not, this is the level we need. You need to know how the input voltage and the output voltage are related. Remember, this is what we measure, the output voltage. I call it VG, or you can call it V out. Different textbook may call it different name. But if we choose like these resistors in a way that the ratio of R3 divided by R1 is equal to R2 divided by RG, if you do the math, you will see that no matter what is the V input, VG will be equal to 0. And this is called a balance bridge, or we say our bridge is balanced. Now, let's say we build these things and we attach the RG, remember the strain gauge, to the component. Now we apply some load, maybe some bending load, some, let's say, tensile load. As a result, this strain gauge, the R value change, right? As you saw in previous slide. And if that change, it means that balance now is not going to be hold, right? Because RG is changing. And the result will be we are going to read some value for G. So if RG, let's say, change, then VG will show some values. And we can use those values and calibrate that. Of course, we need to do some experimental tests. And typically, with every strain gauge we buy, those calibrations are available. So it tells us if, for example, your VG change by 1 volt, it means your strain is that number. So we show some values. We use these values, this value, to calculate strain, which I'll explain to you how. All right. So these are the principle again. All right. Hopefully it's clear. In principle, it's very simple. And again, if you had a chance, perhaps on Friday, I'll bring this strain gauge to the class, and maybe you can check it. Also, I showed another video for you, a short video, which I use a strain gauge with the Wheatstone Bridge. Maybe you can watch that as well. All right. Now, the question is, well, we can use a strain gauge to calculate a strain, a normal strain. Let's say, as I said, a strain which is longitudinal in X and Y direction, right? But what if I want to measure also the shear strain, gamma? Remember, when we have a component, I'm just going to remind you what we had before. Let's say if I have a component like that and apply load on this component, then for any small element on this component, I can measure how much it's changed in X and how much it changed in Y. So if I call these X and Y, then we can calculate epsilon X and we can calculate epsilon Y, perhaps if we know the Poisson ratio, right? Also, we learned before that, let's just bring that element out and show it in a larger shape. That not for this case, but perhaps if we have other loads, maybe if this component is also under torsion, as a result, there will be shear stress. And the shear stress, we learn, is going to change actually the shape of it. If I show it as an exaggerated shape, the shape will be so the shape of this, maybe if I exaggerate it, will be something like that. And there will be a change in that angle. We call that angle gamma. And this is what we call it the shear strain. And we learned that there is a relation between tau and shear strain. So tau is equal to G multiplied by gamma. With G, we call it the shear modulus of elasticity. And for every material, that value is available, right? For every material, we know there is E, the module of elasticity, Poisson ratio, and there is shear module of elasticity, which there is a good relation between them, E to 1 plus nu. That's also a good relation, which we talked about it before. If you forget about it, it's a good time to use it as a review. All right, so that was a review. Now get back to our strain gauge. If I want to measure the shear stress, like tau, I need to know gamma. In order to measure gamma, in order to measure how much, let's say these, if I draw a square on my component, how much is going to change the angle, then I need at least 3 strain gauges, okay? And shortly, we'll see why we need 3 strain gauges. So this is how it works. Let's say this is X direction, this is Y direction. I know it looks like very complicated, but it's not. Just follow me. I need to install 1 strain gauge in direction A. So that 1 strain gauge. I need to put the 2nd strain gauge in direction B. And I need to put the 3rd one in direction C. And I can choose any angle as I wish. So, but we measure this angle with respect to X coordinates. So that's theta A, that's theta B, and that's theta C. I don't go over the proof of this formula. It is available in your textbook or on internet, and you don't need the proof actually. The proof is very long, but this is the relation between epsilon X, epsilon Y, and gamma XY. So gamma XY is here. Epsilon X, epsilon Y, they are there. And remember, we are measuring epsilon A, epsilon B, epsilon C. These are our strain gauge. So the strain gauge measurements. So again, in order to calculate shear stress, we need shear strain, gamma. In order to measure shear strain, we need 3 strain gauges, and we need to put them at different angles, as I showed here, and that's their relation. So you see now, if I know epsilon A, epsilon B, and epsilon C coming from my strain gauges, if I know the angles, because that's the way I glue the strain gauge to the surface, then I can solve these 3 equations simultaneously to get epsilon x, to get epsilon y, and to get gamma xy. All right. Now, as I said, the arrangement of these strain gauges is actually in whatever angle we wish. But typically in practice, we arrange them in a way that the calculation is simpler. For example, why not use theta A equal to 45 and theta B equal to 90, for example, and theta C equal to 180, right? Because then those angles, the cosine and sine, the values are like easier to do the calculation rather than just putting some random numbers there, right? So this arrangement is called a strain rosette. And there are 2 common, like the most 2 common rosette are the 45 degrees and the 120 degrees. It doesn't mean other strain gauges doesn't exist. There are, but these are the most 2 common. So one is the 45 degree. So the 3 strain gauges, we put them like that. And one is 120 degrees, as you see that one, because it makes our calculation easier. The image below, as you see, are actual strain gauges. So keep in mind, this is where we solder our wires like positive, negative, and positive, negative. So we solder our wires there. We glue the strain gauge, and these are the strain gauges. Strain gauge. And similarly for the 120 degree. So typically people put the first one in X direction. So this will go on X direction. And since it's 90 degree, this goes in Y direction. It means your angle with the other one is 45 degrees. Right? So in the formula that you saw above, it means your theta A is 0, your theta B is 45 degree, and your theta C is 90 degree. So the other one is 120 degree. It means your theta A is 0 degree, your theta B is 120, and your theta C is 240 degree. Remember, the angle we measure is always with respect to X. So it means your theta C is 240 degree. Right? Always refer back to that original formula and this original orientation as I showed here. Okay. So here, let me just again stop sharing screen, going back to the camera. I'm going to show you some of these rosette. So going back to my strain gauge boxes, and so I'll have some of these common rosette, which I can show you. This is the 90 degree one. Hopefully you can see it through the camera. Let me bring it down. I need to be careful. So 3 strain gauges, and the orientation is 45 degree, like going that. So another one is the 120. This is the 120 degrees. All right. So, and we have other one, like, for example, in the box that I have here, I have a rosette with only 2 strain gauges. It has only two. Maybe when I need to do the measurement for something that I don't care about the shear strain, only I want an epsilon x and epsilon y, I just use two strain gauge. Sometimes we just use a single strain gauge if we, let's say we have a shaft and we are interested in just one direction. We want to know a stress and a strain in just one direction. If it is in two direction, I use the two perpendicular strain gauge. And we don't have to use a rosette. Maybe if like it happened in the past to me that I didn't have like a rosette like that one. Of course, it makes it easier to work with. Instead, I had a lot of these, so I can glue them separately, each of them independently. So that's in principle the same. All right, so I see a question in the chat. Let me see. How do you use these? So that's a good question. Actually, we just clean the surface that we are interested. Let me just go back. So the way that we use these strain gauges, we clean the surface and then we use epoxy, like any type of glue, but we typically use a good quality glue with as minimal as possible residual, and we glued our strain gauge to the surface. Then after that, we can solder these 2 points to 2 wires, and we get the wires out, and we attach them to the Wheatstone Bridge that I showed you in previous slides. If you are interested, maybe after you've done your exam, actually we have all the strain gauges in the lab. In the past, when we had time, I gave students the bottle of Coke, and I asked each student to attach one of these to the surface. Now it became, and measure the strain when you pop it open, similar to the video that I showed you. If you are interested to try one of these strain gauges, let me know. Maybe after you're done with your exam. And I have a lot of these strain gauges. So let's go back. And it's fun, actually, to try them. And so you will see when you have a component, when you bend it or you apply load, especially if the deformation is large, you will see how a strain gauge shows the value of a strain. Yeah, ask me and I'm happy to show you in the lab. All right, now let's go back. I'm gonna again turn off the camera because I'm gonna... All right, hopefully now you have a sense what is a strain gauge, what is its principle of working, and what is a strain rosette. Okay, now let's solve one problems together. Okay, suppose I have a pressure vessel, and I want to know when the pressure inside is P, and let's say I apply a torque T, then what is the stresses? Of course, you may say, well, if we know the geometry, if we know the material, we can use the formula that we learned in the past to calculate the stresses. Why bother to measure it? Remember, sometimes it's not possible to calculate because we may not know the exact value of T or the exact value of P, or we may not have any information regarding the geometry or the inside of this tank, and calculation is not possible. Or maybe we do, we have all this information, and we just want to confirm if our calculation and our measurements, and they are in accord with each other. All right, let's look at this simple example. Here I have a vessel, a pressure vessel made out of steel, and its Poisson ratio is 0.3, and its module of elasticity is 29, 10 power of 6 psi. And I use a strain gauge with rosette 45 degree, as you see here, and I place X in the hoop direction, as the question explained. So if I showed it here as well, let's say we attach our strain gauge so that this is the X, and this is the Y, and this is the B direction, all right? So this is our actually a strain gauge rosette that we put it there. So that's the, let's suppose that's the A1. And let's say this is the C1, and 45 is the other one. Of course, I exaggerated here. They are typically small, as I showed them to you, and they are not that far apart. But here, for the purpose of discussion, I just showed it like that way. So that's the way that then we arrange our strain gauges. And the question says that you are reading these values for epsilon A, epsilon B, and epsilon C. And we are interested to learn what is the value of stresses, actually. So we want to know what is the sigma X, what is the sigma Y, and what is the tau XY on this pressure vessel. All right. So let's see what sort of information we have. We know epsilon X here is equal to epsilon A because they are in the same direction, right? Our gauge A is reading epsilon X, and that value is 36 10 to the power of minus 6. Remember, it says micron inch per inch, right? So we have that 10 to the power of minus 6. Epsilon typically is a very small numbers. So what about epsilon Y? It's equal to epsilon C, and that value is 150 10 to the power of minus 6 as well, and has no unit. And we know the value of epsilon B, which is 310. Again, 10 to the power of minus 6. We know theta A is 0. We know theta B is 45. Let's just write it down. Theta A is 0. Theta B is 45. And the angle for C is 90 degrees. All right? So we go back to the formula that you just saw. Like here, you should have this formula in your formula sheet for your final exam for sure, because you're going to need them. All right? So if you look at this formula, we'll see epsilon A is not going to give us that much information because theta A is equal to 0. If I put 0 there, so we make the same conclusion as I wrote. Our epsilon A is going to be equal to epsilon X. The same for the last one, epsilon C is equal to epsilon X. So let's use that middle one, epsilon B. All right, so sometimes we may use all three, sometimes like this question, since already epsilon X is equal to epsilon A, epsilon Y is equal to epsilon C, it's a good indication that we only need that epsilon B formula. All right, epsilon B formula, I have to write it down again, is epsilon X cosine squared of theta B, epsilon Y sine squared of theta B plus gamma XY sine theta B and cosine theta B. Let's just substitute this value. So epsilon B is 310, 10 power of minus 6. Epsilon X is 36, 10 to the power of minus 6, and cosine squared of 45. Epsilon Y is 150, 10 to the power of minus 6, sine squared of 45. And then gamma XY, I don't know what's the value, sine 45, cosine 45. So calculation actually is very, very easy because this value is 1 over 2, this value is 1 over 2, this value is 1 over 2. All right. So from here, and I can for now temporarily get rid of this 10 to the power of minus 6. And later I add it to gamma xy. So you'll see the calculation is very, very easy. You don't even need a calculator. So your gamma xy is going to be 4, 3, 4. And remember, we remove it 10 to the power of minus 6. So they have to be all in one order. So that's our shear strain, actually, that we measure here. Shear strain. So we are almost done here. I know the relation between tau and gamma, tau xy, and then here, gamma xy here, which we already calculated. I need the value of g. G is equal to e to 1 plus nu. Question gave me the value for e and the value for nu. So from here, I can find the value for g. I let you to do the calculation. Let me see if I got it. Yes, I did. It gives me 11, 15, 10 to the power of 6 psi. Remember, we have to be consistent with the units. So it means I can substitute that one there. Gamma, we calculated 3, 4, 10 to the power of minus 6. And it should give me here 48, 40 psi. Remember, our units is psi. So that's our shear stress. So now I need to go and find out sigma x and sigma y, right? So I need sigma x and I need sigma y. So remember, we know epsilon x, that's 36, 10 to the power of minus 6. And we know epsilon y is 150, 10 to the power of minus 6. Right? So we know those values. So all I need to do is just use the Hooke law, right? Remember the Hooke law for a 2D, epsilon x is 1 over e sigma x minus nu sigma y, and epsilon y is 1 over e sigma y minus nu sigma x. So let's substitute this value quickly. So it's going to be 36, 10 to the power of minus 6, 129, 10 to the power of 6, sigma x 0.3, sigma y. And what about this one? 150, 10 to the power of minus 6, 129, 10 to the power of 6, sigma y minus 0. X. All right. So again, the calculation for this one should be very easy. Remember, 10 to the power of 6, 10 to the power of 6 here. They multiply to each other and they cancel out. So it seems our equations become simpler. I strongly recommend you do like the practice problem that I'm just going to introduce. You do it once, do the old calculations so you become comfortable with this sort of calculation. So if you see a question in the exam, you can easily solve it. So I'll simplify my equation, sigma y 0.3 sigma x equal to 4350. I have two simultaneous equations and two unknown. Simply we solve them. And these are the value that I got, but please check that, do your own calculation for all the things that I did here. I might have done a mistake because I just did the calculations quickly before your class starts. So here we got everything that we need, right? We managed to get our sigma x and sigma y, and we managed to get our tau xy here as well. So let's just put it in the box. So this is our tau xy, which is 4840 psi. So using 3 strain gauges, we get these values. All right. Now I have one quick question for you, which you can type in the chat or think about it. Here we have a pressure vessel, guys, right? And a pressure vessel, if you recall, in a pressure vessel, if I call this one X and I call this one Y, or we call this one the hoop, the axial direction, and we call this one the hoop direction, hoop stress. If you remember, we had a formula for these, right? Let me write down the formula. Hoop, sigma hoop was, which here is for us is sigma Y, is PR divided by T. And sigma X, the axial, sigma X is PR divided by 2T. So we learned before that sigma Y is always 2 times of sigma X. X here. Like the hoop stress is twice as the axial stress. So here, if I check these values, oh, here I wrote sigma. This is sigma Y. All right, so please correct that one. This is sigma Y. Here, if I check this one, if I divide sigma Y by sigma X, I get 199. Like my sigma Y is not twice as sigma X, a little bit close. Why is that? Can you type in the chat? Why do you think we did not get the exact value of 2? Did we make a mistake somewhere? Or we'll write the exact numbers here for you. It is, even I round it a little bit, it is 985. 985 instead of 2. Why not 2? So why do you think is the cause of this discrepancy? Because here is the theory, right? In theory, we know that this relation should hold, but here we have like a little bit of discrepancy. Let's look at your answer in the chat. And all right. So would there be a component from strain angle B in the EX and EB calculation? There is not, right? You saw it in the formula. Yeah, so I saw some answer. Exactly. So some of you wrote here, of course, during calculation, I did some rounding here and there. But beside that, remember, always when you do the measurement, there is always some errors. So in measuring, we cannot get the exact values. Okay, so we can talk about it later. Here, I just have one question for you, which I'm going to post it on Canvas, and you need to do it before the class start on Friday. Okay, let's just quickly go over it in 1 minute, and we are done with the lecture today. So suppose your friend decide to do a different strain gauges. They don't like the 45 gauges, and they use the 120 gauges. And they did some reading, and now they want to compare their reading with the value that you got, okay? So the question says that now that you managed to calculate and know that epsilon x, epsilon y, and gamma xy from your friends share his information with you, they are all PSI, and this is PSI, and gamma xy, 4840 PSI. So what is the value of epsilon A, epsilon B, and epsilon c that your friend using this strain gauge is going to read. So they're going to compare their numbers with yours to make sure that none of you have done a mistake. So please complete this assignment before the class starts on Friday, and I will post the annotated slides, and I will send an announcement, and I will make the assignment on Canvas as well. Okay, and also I will post the recorded lecture on Canvas in case you wish to review one part, or maybe in case you miss a part and want to rewatch. Okay, so with that, I'm going to stop actually recording. Let's stop it, but I'm happy to answer any question that you have.